In this particular case, that they have MOSFET to ground, current sense transformer feed into the controller, and then they have a second stage that's identical to the first stage. Current says the controller is a UCC 28070, and basically these guns are operating 180 degrees out of phase. Yes?
What is the power MOSFET driving a capacitor? Switching capacitor?
I'm sorry, I'm half deaf. Let me get closer.
The right side of that picture.
Okay, the right side.
What was that power MOSFET?
Ah, that power MOSFET, that's the one that gets me in trouble. So the question is, what's that MOSFET over here? And so when you first turn this thing on, you know, they snap the input voltage on. This capacitor is the bulk cap on the output of the power supply. And what happens is, if that resistor wasn't there would be a big spike of current going through the capacitor. And so you'd have a big surge current on the primary. And so what they're doing here is not allowing that. They're going to put a capacitor in series with the bulk. I'm sorry, they're going to put a resistor in series with the bulk capacitor. So when you first turn on that voltage, all the input voltage shows up across the resistor. They charge up the capacitor, and then when there's basically zero voltage on the resistor, they turn the MOSFET on. And then the idea is now you have a low resistance connection to the capacitor, and it's charged up, and now your PFC can operate normally. And so, yes. No, okay, all right. So, but I had a question, and so I've been kind of ignoring this capacitor because I didn't know the answer, and I still haven't found out. But somebody said, well, you better watch that when you do surge testing. And so I'm going to say that. You better, if you do this, you better watch it when you do surge testing. Because there's going to be some resistance that's associated with this capacitor, and there could be a fairly large amount of current that comes through here when you have a surge on the input. So just watch it. And I guess that's it. So that's kind of block diagram. Like I said, the detailed schematics of this are all available on the TI server. So help yourself if you're interested. I guess a couple of points about the component selection on the power correcting board. You want to have fast MOSFETs just because you want to get those diodes recovered in a hurry. And then there's kind of a rule of thumb, and it's kind of interesting that in your MOSFETs you want to have about 50% switching losses and 50% conduction losses. And you kind of think of it in a real simple way. If you drew a little curve that had maybe die area on the bottom of the curve, one that had losses on the vertical portion of the curve, and you plotted conduction losses, you would start with a very large amount of conduction losses at a small die area, and as you increase the die area, the losses would go down. It just goes down as one over the area, basically. And then you can plot another one that has switching losses. It's zero die area, you're not going to have any switching losses. And then as you increase the die area, the switching losses will increase directly with the area. And then you can plot the sum of the two, and what you're going to find is that the minimum occurs when the switching losses are equal to the conduction losses. So that's a nice rule of thumb, because I've seen people with a relatively large MOSFET put a smaller MOSFET in its place and actually reduce the power dissipation of the power supply because they had too much switching loss, because the devices were too slow, or they had too much output capacitance. So I guess the next point is, since you do have an issue with the fast recovery diodes, maybe you want to look at an alternative technology. In this particular case, they propose silicon carbide. Silicon carbide, probably 5 years ago, had lots of reliability problems. And more recently, it's been vastly improved. It still has a cost penalty, but it gets you this 2% increase on efficiency. And so that may be worth a trade. Okay. And then results in a power stage efficiency of 97% at high line. Well, that's pretty good. So we're 98, 99% efficient in rectifiers. We're 97% efficient in the PFC. And so here's a curve showing the efficiency of the PFC at low line and then at high line also. And you can see the PFC by itself is quite good at low line. You can see that we're up in the 98% range at maximum load at low line. You can see with the high line case that our losses our efficiency kind of degrades at light loads because of the switching losses in the power supply. Again, they took the PFC and added the EMI filter to it and made made emission measurements, and they had lots of margin in the PFC design at about 300 watts of output power. All right, so for the power stage, they used the phase shifted bridge. So has anybody used phase shifted bridges here? No. Okay. So in a traditional full bridge converter, you have 4 MOSFETs like this, and you operate them in pairs. For instance, you may turn A and D on, and that puts the transformer voltage across, that puts the input voltage across the transformer. And that gets reflected to the secondary, and you rectify it in the secondary. You turn them off, and the output inductor drives the voltage on the transformer to 0. And so then you turn these other MOSFETs on, B and C on, and it puts a voltage across the transformer in the opposite direction, so you balance the flux in the transformer, and you rectify that, and you control the output voltage by controlling the conduction angle on the opposing switches. The phase shifted full bridge is a little different. It operates the 4 power switches independently. For instance, you might start with A and D on, and then you turn A off. And what happens is the current in the output inductor drives this node from the positive rail down to the negative rail. And since you have the current driving this capacitance here, there's no dissipation associated with it. And so you have a lossless transition from the top rail down to the bottom rail. And then after you made that transition, you turn MOSFET B on, and it conducts. And then at some later time, you'll still have some current flowing there. You'll turn D off, and the current flow will drive this voltage toward the positive rail. And then you kind of go through the sequence again. So basically, these switches, A and these switches, when you have the opposing switches on, they put the voltage across, they put the input voltage across the power transformer for the A and D and C and B cases. And the other times that you have 0 voltage on the transformer, and you just basically control the phasing between the 2 sets of MOSFETs.